let's talk a little bit about the existence and uniqueness of inverses. So here on the screen, I have up the definition of an invertible matrix. And what we notice is that all it's saying is that we just have to find some B if there is a matrix such that A times B equals B times A equals the identity, in which case we call B an inverse. Right? So straight off the bat, we don't know that there's only one. We just need to find one. So for example, let's take the matrix A to be 1, 2, 3, 4. This is invertible because we can multiply it by a matrix B, which in this case is going to be -2, 1, 3 halves, -1 half. Then when we multiply A times B, all right, so 1, 2, 3, 4 times -2, 1, 3 halves, -1 half. All right, I'm going to leave the steps of multiplying that to verify this to you. All right, we get the identity matrix, and when we go the other way around, B times A, with B coming first, we also get the 2 by 2 identity matrix. So these are two things we need, and so now we know that A is invertible. But the weird thing is that this doesn't guarantee that B is the only matrix that'll do this for us. So we might ask, put this note here, we might ask if there is some C for which the same holds. A times C equals C times A equals the identity. Now here we scroll down, theorem 2.7 says if A is invertible, then its inverse is unique. So theorem 2.7 says that there's not a different C. C is actually equal to B. So let's go ahead and see if we can verify that. So let's check. All right. So let's go ahead and assume A times B equals B times A equals the identity like we had above. And let's assume that we have another one. A times C equals C times A equals I. All right. So our goal, what theorem 2.7 says, is that B equals C. So our goal of what we want to show is that B equals C. All right. So let's go ahead and try and show this. So let's compute starting with B and do just like we did in the last proof we saw in the video. We want to go through steps to logically get to B equaling C. So the way we're going to do this in this case is B equal to B times I, we know, and this is from theorem 2.4 property 1. If you want to go back and look, this is exactly what that theorem says. All right. And the reason I introduced I is because we know a relationship between A times C and I. All right, so let's go ahead and replace I by A times C. So this is going to be substitution using our assumption. All right. But now look, B is pretty close to A, and when B multiplies by A, we get the identity matrix back. So let's go ahead and rearrange this so that we're going to be able to do that. So this now, we want to again justify this. This is theorem 2.3, number 1 allows us to rearrange parentheses in multiplication. All right. And now the B times A, these are next to each other. So we can again do another substitution. So this is I times C, again by substitution, using our assumption. And then lastly, we do want to add in this step. This is the same thing as C, again, by theorem 2.4, property 2 this time, because the identity is on the opposite side of C. Okay, so therefore, B is actually equal to C as desired. So thus, B equals C as desired. And in fact, maybe I've tricked you, maybe you've known it all along, we just did a proof of theorem 2.7. Because there was no point in here that we actually used the definition of A from our example above, or the definition of B from above. So the proof that we just wrote down works in general for any matrices A, B, and C. All right, excellent. Enjoy!